Imagine a spacecraft accelerating in deep space, engines burning with relentless precision, pushing it faster than anything humanity has ever built. 10% of light speed, 50%, 90%. Each milestone would represent a revolution in physics and engineering, and then it approaches 99.999% of light speed. At first glance, that number feels like triumph, almost ultimate motion, almost cosmic freedom. Yet at this threshold, something profoundly unsettling begins to happen. Speed stops behaving like speed. In everyday experience, motion scales smoothly. Drive twice as fast, arrive in half the time, throw harder, the ball travels farther. Intuition suggests continuity. But near light speed, intuition collapses. The universe does not respond proportionally. It reshapes itself around velocity. Time begins to stretch, space compresses, energy swells dramatically. What appeared to be progress through space becomes a transformation of space and time themselves. The speed of light in vacuum is approximately 299,792 kilometers per second. That number is not simply large, it is foundational. It appears in Einstein's equations not as a measurement of photons alone, but as the conversion factor between space and time. As velocity approaches, this constant relativistic effects intensify. The Lorentz factor, which governs time dilation and length contraction, rises sharply. At 99% light speed, time on board slows to roughly 1/7 of that experienced by a stationary observer. At 99.9%, it slows to about 1/22nd. At 99.999%, the slowdown becomes extreme. Seconds for the traveler correspond to hours outside. You might assume this is an advantage. After all, time dilation suggests that interstellar voyages could feel shorter to those aboard. However, this apparent gift conceals a deeper reality. The closer velocity approaches light speed, the more violently space-time resists further acceleration. The relationship between speed and required energy ceases to be linear. It becomes asymptotic. Picture a curve that rises gradually at first, then steepens dramatically, climbing almost vertically as it nears a boundary it never reaches. That curve describes the energy required to accelerate mass toward light speed. Moving from 50% to 60% demands a manageable increase. Moving from 90% to 99% requires vastly more, but pushing from 99.9% to 99.99% demands an almost unimaginable escalation. Each additional fraction of velocity multiplies energy requirements disproportionately. At first glance, 99.99% seems indistinguishable from 100%. It feels like practical completion. Yet physics treats that final fraction as infinite distance. No object with mass can reach light speed because doing so would require infinite energy. The barrier is not technological, it is mathematical, embedded within the geometry of space-time itself. And there is more. As velocity increases, space contracts in the direction of motion. From the traveler's perspective, distances shrink. A journey to a star system several light years away appears compressed. Yet from an external frame, nothing shortens. Reality splits into perspectives, each internally consistent yet mutually distorted. This is where speed becomes something else entirely. It stops being a measure of motion and becomes a confrontation with the architecture of the universe. Time decouples from shared experience, space warps, energy surges toward infinity. What once seemed like the ultimate expression of technological mastery transforms into an encounter with limits woven into existence. At 99.999% of light speed, you are not simply moving faster than ever before. You are entering a regime where the familiar rules of intuition dissolve. And beyond that threshold lies not freedom but the uncompromising structure of reality itself. If speed begins to distort reality, time is the first casualty. At low velocities, time appears universal and shared. Seconds tick uniformly. Clocks agree. Cause follows effect in predictable rhythm. But as velocity approaches light speed, this shared temporal structure fractures. What remains is not a single flow of time, but multiple coexisting rates of duration. Einstein's theory of special relativity provides the mechanism. The Lorentz factor, written as gamma, determines how time dilates as velocity increases. It is defined as 1 divided by the square root of 1 minus v squared over c squared. At everyday speeds, the difference is negligible. But as velocity approaches c, the denominator shrinks and gamma grows rapidly. At 90% of light speed, gamma is approximately 2.3. That means time aboard a spacecraft passes at less than half the rate experienced by an observer at rest. At 99%, gamma rises to about 7. At 99.9%, it exceeds 22. At 99.99%, gamma climbs to roughly 223. This means that for every year experienced by travelers, more than 2 centuries pass on Earth. You might assume this is advantageous. From the crew's perspective, long voyages become compressed. A journey lasting hundreds of years externally might feel like months internally. Yet this benefit carries a hidden rupture. Civilization depends on shared time. Economies, communication, culture, and coordination all assume relatively synchronized clocks. Near light speed, synchronization dissolves. Imagine departing Earth at 99.99% of light speed toward a destination 10 light years away. From Earth's frame, the trip would take just over 10 years. But on board, due to time dilation, the journey would feel dramatically shorter, perhaps only weeks. Upon arrival and return, travelers might discover centuries have passed at home. Generations replaced. Languages evolved. Political systems vanished. Relativity does not merely slow aging, it separates histories. At first glance, time dilation seems like a curious side effect of extreme speed. In reality, it reflects a deeper principle. Space-time adjusts to preserve the invariant speed of light. If light's velocity is constant in all inertial frames, then time and space must transform accordingly. The universe maintains consistency by sacrificing simultaneity. Simultaneity itself becomes relative. Two events that appear simultaneous from Earth may not be simultaneous from the spacecraft's perspective. The faster the motion, the more pronounced the disagreement. This is not illusion. It is structural. Reality has no universal clock ticking in the background. Consider another implication. Suppose two identical twins separate, one remaining on Earth and the other traveling at 99.999% of light speed for a brief subjective duration. Upon reunion, the traveling twin would be far younger. This is not paradoxical. It is experimentally confirmed in principle. Particles accelerated to near light speeds and particle accelerators exhibit measurable time dilation. Muons traveling through Earth's atmosphere survive longer than stationary calculations would allow because their internal clocks run slower relative to us. At 99.999% of light speed, the effect becomes dramatic. The universe divides into frames of reference that no longer agree on duration. Personal experience decouples from collective chronology. The faster one moves, the less aligned one remains with the rest of existence. You might imagine that advanced technology could compensate for this separation. Yet no engineering solution can restore a universal clock. The divergence arises from geometry itself. Time dilation is not a malfunction. It is the cost of preserving the constant speed of light. And this is where the terror deepens. Near light speed, motion does not merely transport you across space. It detaches you from shared time. The faster you go, the less you belong to the temporal fabric of those you left behind. Civilization depends on continuity. Relativity fractures it. At 99.999% of light speed, you are not simply traveling quickly. You are stepping outside the synchronized rhythm of your species. Time does not stop, but it ceases to be common. And once time becomes relative, the idea of collective progress begins to dissolve. If time fractures first, energy delivers the second and more brutal revelation. Moving at 99.99% of light speed is not merely a matter of advanced propulsion. It is an encounter with a wall disguised as a curve. The mathematics does not gently resist further acceleration. It explodes. In classical physics, kinetic energy increases with the square of velocity. Double the speed, and energy rises by a factor of 4. The relationship is predictable and manageable, but relativity replaces that simplicity with the Lorentz factor. As velocity approaches the speed of light, the factor grows without bound. The kinetic energy required is not proportional to speed. It diverges asymptotically. At 99% of light speed, the Lorentz factor is roughly 7. That means the relativistic energy is 7 times the rest energy of the object. At 99.9%, the factor exceeds 22. At 99.99%, it rises above 200. Each additional decimal place toward light speed demands vastly more energy than the last. The curve steepens sharply, climbing toward infinity without ever reaching it. You might assume that with sufficient fuel, perhaps antimatter or advanced fusion, this barrier could be overcome. Yet even antimatter obeys E equals mc squared. Converting 1 kilogram of matter entirely into energy yields about 9 times 10 to the 16 joules. That is enormous. But accelerating even a modest spacecraft to 99.99% of light speed would require energy on the scale of global annual energy consumption multiplied many times over, and that calculation ignores inefficiency, shielding, life support, and structural mass. Imagine a vessel weighing 1,000 metric tons, including fuel and infrastructure. Its rest energy alone, determined by mass times c squared, is staggering. To push that mass to 99.99% of light speed would require hundreds of times its rest energy. That is not a minor engineering challenge, it is a planetary scale demand. Entire civilizations would have to redirect their energy production toward propelling a single craft. At first glance, 99.99% appears tantalizingly close to 100%. The difference seems negligible, yet physics treats that remaining fraction as infinite distance in energy space. No finite fuel supply can bridge the final gap. The closer velocity approaches light speed, the more each incremental increase costs. There is no plateau, no stabilization, only escalation. And the problem compounds. To carry more fuel requires more mass. More mass requires more energy to accelerate. That additional energy demands more fuel. Still, the system becomes recursive. The rocket equation, already unforgiving in classical regimes, becomes merciless under relativistic scaling. Each solution introduces new mass, which introduces new energy demand. You might argue that perhaps unmanned probes could accept such costs, but even small objects experience the same asymptotic curve. The limit does not discriminate between human crews and robotic payloads. The divergence is structural. There is also a deeper conceptual shift. In relativity, as velocity increases, momentum increases beyond classical expectation. The object resists acceleration, not because its intrinsic mass changes in a simple sense, but because space-time geometry alters the relationship between force and motion. The universe itself resists further increase in velocity. Consider pushing a massive object up an increasingly steep hill. At first, progress is steady, but as the slope approaches vertical, each additional step requires disproportionate effort. Near light speed, the hill becomes nearly vertical. The final fraction is not a small incline, it is an infinite wall. This is the energy catastrophe. At 99.999% of light speed, you are not near completion. You are near divergence. The equations reveal that light speed is not a destination awaiting arrival. It is a boundary approached but never touched. And this transforms the dream of extreme velocity into something sobering. It is not that humanity lacks ambition. It is that the universe imposes arithmetic that does not yield. The faster you attempt to move, the more violently reality resists. Speed ceases to be a matter of engineering prowess and becomes a confrontation with infinity itself. If time fractures and energy diverges, there is another consequence that is even more immediate. At 99.99% of light speed, the universe itself changes character. What appears empty becomes lethal. What seems harmless becomes destructive. Space does not remain a silent vacuum. It transforms into a storm. At first glance, interstellar space appears almost perfectly empty. The density of matter between stars is extraordinarily low, often just a few hydrogen atoms per cubic centimeter. Compared to Earth's atmosphere, that is negligible. One might assume that traveling through such sparse regions at extreme velocity poses little resistance. However, velocity changes everything. At 99.999% of light speed, even a single hydrogen atom becomes a projectile of enormous energy. From the spacecraft's frame of reference, those atoms are no longer drifting gently. They are approaching at nearly light speed. Relativistic kinetic energy scales with the Lorentz factor. What was once a tiny particle becomes effectively high-energy radiation. Consider a single proton at rest in interstellar space. Relative to a spacecraft moving at 99.99% of light speed, that proton's energy increases dramatically. It behaves like a subatomic bullet. Collisions at these velocities do not resemble mild impacts. They resemble particle accelerator events. The hull of the spacecraft would be bombarded constantly by a stream of high-energy particles. You might assume shielding could solve this. Add thicker material. Reinforce the structure. Yet shielding adds mass, and mass increases energy demands for acceleration. Furthermore, high-energy particles interacting with shielding materials generate secondary radiation. Gamma rays, neutrons, and particle cascades would be produced inside the protective layers. The shield itself becomes a source of danger. There is also the cosmic microwave background, the faint afterglow of the early universe. At rest it is harmless, a microwave radiation field at about 2.7 Kelvin. But at relativistic speeds, this background radiation becomes blue-shifted. Photons striking the spacecraft from the forward direction gain energy due to Doppler shift. At sufficiently high velocities, even microwave photons shift into higher energy ranges, potentially into X-ray or gamma-ray frequencies. At first glance, the vacuum of space seems peaceful. In reality, near light speed, the vacuum becomes a radiation bath. The faster you move, the more violent it becomes. The emptiness transforms into a continuous barrage. Even microscopic dust grains pose catastrophic risk. A grain of interstellar dust weighing a fraction of a milligram may seem trivial. Yet at 99.999% of light speed, its kinetic energy rivals that of an explosive device. A collision would release enormous energy upon impact, vaporizing material and sending shock waves through the structure. Detecting and avoiding such particles at relativistic velocity is nearly impossible. By the time sensors register a threat, interaction has already occurred. You might imagine sophisticated deflection systems, electromagnetic fields, or laser sweeps clearing the path ahead. But every protective measure consumes energy and adds complexity. Each addition compounds the energy catastrophe described earlier. The faster the spacecraft travels, the more hostile its environment becomes. This is the hidden violence of extreme velocity. It is not merely that energy demands approach infinity. It is that the medium through which you travel ceases to be benign. The universe does not remain static as you accelerate. Relative motion alters the behavior of matter and radiation. At 99.99% of light speed, space is no longer empty. It is transformed by relativity into a high-energy frontier where atoms strike like cosmic bullets, and background radiation sharpens into beams of energetic photons. Survival becomes not only an engineering challenge, but a confrontation with physics at its most unforgiving. Speed, which once symbolized freedom and progress, now reveals its darker side. The closer you approach light speed, the more violently the universe pushes back, and beyond this threshold lies not open exploration, but a domain where motion itself generates danger from the very fabric of space. By the time a spacecraft approaches 99.99% of light speed, the dream of ultimate motion has transformed into something far more sobering. Time fractures, energy diverges, space contracts, the vacuum turns violent. What began as a triumph of engineering becomes a confrontation with the architecture of reality itself. And the deeper realization is this: light speed is not simply a high number. It is a boundary built into existence. At first glance, pushing closer to light speed feels like progress toward transcendence. Humanity has always associated speed with mastery. Faster travel means shorter distances. Faster communication means stronger connection. In that narrative, approaching light speed appears to be the final technological victory. Yet physics quietly overturns this assumption. The closer one moves toward the ultimate limit, the less conventional progress applies. Gains diminish while costs explode. You might assume that a sufficiently advanced civilization could overcome these challenges, perhaps through unimaginable energy generation, exotic matter, or new physical discoveries, but the speed of light is not a temporary obstacle waiting for refinement. It is embedded in relativity, electromagnetism, and the structure of space-time itself. It defines how cause and effect unfold. To surpass it would not require better engines. It would require rewriting the universe. The terrifying truth is not that we lack ambition. It is that reality contains structural ceilings. Near light speed, every improvement demands disproportionate sacrifice. A civilization attempting to operate routinely at 99.99% of light speed would need planetary-scale energy, unprecedented shielding, and acceptance of temporal dislocation. Travelers would return to societies unrecognizable. Communication across vast distances would lag irreversibly. Coordination would fragment. At first glance, extreme velocity promises escape from cosmic isolation. In reality, it intensifies isolation. Time dilation separates travelers from their origin. Causality restricts communication. The energy cost concentrates resources into singular, fragile endeavors. Instead of expanding seamlessly across the stars, civilization becomes segmented into relativistic enclaves. Consider the broader implication. The Milky Way contains hundreds of billions of stars. It is tempting to imagine that advanced life, once emerging, inevitably spreads across such abundance. Yet if the speed of light enforces escalating energy costs and violent environmental conditions at extreme velocity, then large-scale galactic integration becomes improbable. Not impossible in principle, but profoundly constrained in practice. This realization reframes the meaning of advancement. Perhaps expansion is not the ultimate metric of civilization. Perhaps depth of understanding matters more than breadth of territory. Within the light speed boundary, extraordinary achievement remains possible. Mastery of planetary sustainability, deep comprehension of physical law, refinement of knowledge and culture, these pursuits do not require violating relativity. The universe does not appear hostile at everyday scales. It permits stable atoms, predictable chemistry, and coherent physical law. The same constant that limits speed also stabilizes structure. Without it, causality would fracture and the cosmos would lose consistency. The boundary that frustrates ambition simultaneously preserves order. You might see this as confinement, yet boundaries define form. A melody requires limits on frequency to be recognizable. A structure requires constraints to remain standing. In a similar way, the speed of light shapes the cosmos into a coherent system. It restricts motion, but it also enables stability. At 99.99% of light speed, the illusion of escape dissolves. The universe reveals that freedom is not measured by velocity alone. True power lies not in outrunning physical law, but in understanding it. The terrifying truth is not that we cannot reach ultimate speed. It is that ultimate speed was never meant to be reached. The closer we approach that boundary, the clearer the message becomes. Reality is structured. Ambition must align with that structure. And within those constraints, there remains something profound, the capacity to comprehend the laws that govern everything, even if we can never outrun them.